So we're going to talk for a second about solving exponential and logarithmic equations. So exponential equations are equations where we end up with, some variable in the exponent, right? There could be other terms. We could have a constant over here, but the main identifying point of an exponential equation is we're dealing with an equation that has the variable x in the exponent. Similarly, for logarithmic equations, we might be dealing with, a logarithm that has a variable in the argument. Okay, so we would be isolating and trying to solve for that x. So we want to know, what an exponential equation looks like. It has the variable in the exponent, and a logarithmic equation has a log in it with a variable in the logarithm. So we have two basic equation solving principles, and I'm going to detail each of those for us. The first of our basic equation solving principles is a base exponent property. And what the base exponent property says is if I have an exponential equation, two bases, maybe x to the b equals x to the y. All right, and so this is for any base that's positive and not equal to 1, because remember those are outside of the domain of exponential equations. So the base has to be positive and not equal to 1. If we have an exponential equation and we have the same base on the left equal to the same base on the right, and they're both raised to a different exponential power, then what we can say, this is a biconditional statement, so we go both directions, is that x would equal y. If the bases are the same, then the exponents are going to be equal to each other. So essentially we can just drop those bases, but you have to have one base equal to one base. Okay, it has to be only one. And if you have one base equal to one base, then you can drop the bases. Or going the other direction, if you have an equation, then you can exponentiate, is what we call that. Exponentiate each side. So you could go the reverse direction and taking a regular equation, create something that's exponential. We don't do that as much, but that's an option. So when we have this double-ended arrow that I've got here, that means it's a biconditional statement. It reads as if and only if, and means we can go in both directions. So my other equation here is my logarithmic property of equality, and this is very similar, and it just says that if we have 1 log base b of some x value equal to 1 log base b of some y value, then again we have a biconditional statement. If we have 1 log equal to 1 log, we can drop the logs and state that that x argument would be equal to the y. So we can come over here and say, well, x equals y. So if we have 1 log equal to 1 log, we can drop the logs. Or if we have an equation going the opposite direction, we can take the log of both sides. Take the log of both sides. Okay, so we've got these two properties here, and we can use them in either direction. More commonly, what we'll be doing with exponentials would be dropping that base on either side. And then with the logarithms, again, if you've got 1 log equal to 1 log, we can drop those logs. So let's look at some basic equations to solve. We have 4 basic types of equations. We have exponential bases relate, and then we have an exponential bases do not relate. So I'm going to detail each of these 2 types of exponentials, and then we have 2 types of logarithms. And the main thing we want to think about with these equations or these solving techniques, I should say, is like when we're solving a quadratic equation, we first try to factor because factoring is easier. But if we can't factor, we have a longer process which always works, which would be the quadratic formula. So in these situations, we've got two methods. We've got kind of our easier method, simplify it and, get rid of the bases, or the long method where we have to use logarithms to solve. Okay, so an example of something that might be exponential, bases relate, might be if I had 8 to the x equals 32. Okay, so when we think about this, we're always thinking about bases and remembering that exponential equations, we've got these base values, and we want to think about those bases as being powers. So 8 is 2 cubed, and 32 is 2 to the 5th. So these are both base 2. So my first step, looking over here, and there's a typo, but I am not in my office and can't fix it. Step A says we use the properties of exponents to write this as 1 base equal to 1 base. So I'm going to rewrite this as 2 cubed to the x equals 2 to the 5th. And that can be simplified because a power to a power we multiply. So I have 2 to the 3x equals 2 to the 5th. So now that I have 1 base equal to 1 base, I can drop the base on either side and just let those exponents be equal to each other. So this would become 3x equals 5, or x equals 5/3. Okay, so if we use our properties of exponents, we can simplify it and create a pretty easy to solve, generally linear or quadratic equation. And then we always want to make sure we check. So if I went to my calculator and I typed into my calculator 8 to the 5/3, the calculator should give me an output of 32. All right? So the easier way to solve an exponential equation is, when we can write them as 1 base equal to 1 base. But we can't always do that. So we have a method that works in situations where we can't do that. So an example of that we have right here. Exponential bases do not relate. So this is kind of like the difference between, again, factoring and quadratic formula. The last one was factoring. We could manipulate it. It was easier. This one's like the quadratic formula. We might have to make it look more complex in order to solve it. Okay, so again, we want to make sure we have it simplified to 1 base equal to 1 base. And when I start this problem, I'm going to write it that way. So we might have a problem 3 to the x equals 10. Now, I have base 3 on this side, and I know my powers of 3. I've got 3, 9, 27, 81, and none of those are a power of 10. So I can't write either side of this as, a base similar to the other side. So in this situation, since it's already 1 base equal to 1 base, I'm going to either take the log or the natural log of either side. So the common log, remember, is base 10. The natural log is base e. In this situation, because I have a 10, I might lean more towards my common log as opposed to natural log. But really, you can do it either way and you'll get the exact same answer. So in this situation, I'm going to take the common log of either side. Now, the common log of 10, what's nice about that is that simplifies to 1. So I have log base 10 of 3 to the x equals 1. So I might have left that as log of 10. If it had a different number, it would probably still have a logarithm in there. So we've taken the log of both sides. The next step is we're going to use the power rule of logarithms. And the power rule of logarithms says I can take that power and write it in front as a product. So this is x times the log of 3 equals 1. And so solving for x, I can divide on both sides by log 3, and I've got x equals 1 divided by log 3. And that is my exact answer. So I have some steps here. We didn't do all of those steps. We didn't distribute, we didn't collect, we didn't factor, because this was a pretty basic problem. So sometimes we skip those steps. But generally, those steps are always going to occur in that order. In this situation, we used the power rule, and then we divided to get our exact answer. So again, sometimes one of these steps here in the middle may be skipped. And we can write that as an approximate answer. Typing that into my calculator, I get approximately 2.09590. Okay? And then you want to make sure it checks. So you can always take that and plug that directly into your calculator. If I were checking this, I would say 3 to the 1 divided by log of 3. And that should give me an output of 10. All right, so 2 more quick examples. Let's look at 2 types of logarithm problems. We can have a logarithmic equation which simplifies to 1 log equals 1 log. So this is kind of like my factoring version as opposed to the quadratic version, which would be longer. So if you can write it as 1 log equal to 1 log, what's nice is we can drop the logs. Okay, so but of course that's contingent on writing it as 1 log equal to 1 log. So we'll do a really basic example here. Maybe I have log base 2 of x equals log base 2 of 5x plus 1. So in this situation, I have 1 logarithm equal to 1 logarithm. Sometimes we have to use properties of logarithms, and so we'll do some further examples about that later. But right now, we just want to see how this property of logarithmic equality works. So if I have 1 log equal to 1 log, I can drop the logs on either side, and I can simply say, well, this is x equal to 5x plus 1. So now I have a linear equation. Of course, sometimes it could be quadratic or rational, but we need to solve this resulting equation. So I'll subtract 5x from both sides. I have negative 4x equals 1, and divide by negative 4 on both sides. X equals 1 over negative 4. So this is my final answer. X equals negative 1/4 or negative 0.25. And I'm done. Well, not quite, because we do need to make sure that we remember to check. So if I check this, and I tried to plug that in, log base 2 of negative 0.25 or negative 1/4, my argument is negative. And what we previously learned about logarithms is that the argument cannot be negative. It's not allowed. So in this situation, we end up with a problem that has no solution. This solution we're looking at here is extraneous. My final answer would be no solution. All right, so sometimes when you're working through these, you may have one answer that doesn't work out of 2. Maybe neither of them work. Maybe both of them work. All right, but it's very important to check because negative numbers are outside of the domain of what we have defined for logarithms. Okay, you cannot have a negative argument, or you can't take the log of a negative number. So let's look at our last example here. So in this situation, we're still dealing with a logarithmic equation, but this is something that might simplify to a log equals a number. And of course, you can always make a logarithmic equation equal to a number, even if there isn't a constant in there, because you can rearrange any equation and make it equal to 0. You can just move all of the terms to one side of the equation. All right, so our goal, if we were doing log equal to a number, would be to write this as 1 log equal to a number. Once we've done so, then we can convert to exponential form. And we did a lot of practice with that previously in this unit. So we would convert the logarithm to exponential form. At this point, we'll have an equation that we can solve. It's normally linear, quadratic, could be rational. And then finally, we have to remember to check. So let's look at an example of this type. The natural log of x plus 2 equals 10. So you can clearly see that I have one logarithm on the left equal to a number 10 on the right. So once I have it as 1 log equal to a number, I can convert it to exponential form. Now here we have natural log, and we want to remember that natural log is log base e. So I have log base e of the quantity x plus 2 as my argument is equal to 10. Converting that, my base is always there, and then that 10 and the x plus 2 are going to switch sides. So I've got e to the 10 equals x plus 2. E to the 10th is a number. E is Euler's number, approximately 2.718. So if I'm trying to solve for x, all I need to do is subtract that 2. And this would give me e to the 10th minus 2 equals x. So this is my exact solution. And if I were to type this in my calculator to get an approximate solution, my calculator would return 22,024.46579. So this is approximate. And of course, when you guys are working on your homework to approximate, you're going to be entering something into the computer. So it's going to ask you to give an approximate solution and round quite often. So we're done talking about solving our basic types of equation, and then now I'm going to break off into a couple videos showing you more examples of solving exponential and more examples of solving logarithmic equations.